My name is Olivia Soghomonian, and I'm an undergraduate here at Fresno State University, and I'm going to be giving a talk on a characterization of convergence in Banach spaces with a Schauder basis. And my research advisor for this was Dr. Mara Markin. So the method in the present paper is abstract and is phrased in terms of Banach spaces, linear operators, and so on. And this has the advantage of greater simplicity in proof and greater generality in applications. So by looking at specific cases of convergence, we can develop a general characterization of convergence in Banach spaces. And we can do this by extending the well-known characterizations of convergence in the spaces LP of p-summable sequences and in the space C0 of vanishing sequences to a general characterization of convergence in a Banach space with a Schauder basis. And the results of this were recently published as well. So for some preliminaries, we have that a norm vector space is a vector space X over the scalar field of real or complex numbers with a norm or mapping to the real numbers as shown here. And it's subject to the following norm axioms, which are non-negativity, separation, absolute scalability, and sub-additivity. And then the norm generates the norm metric on X. And so for our examples, we have the space LPN and LP, where in the first case of LPN, we have a space of ordered n tuples of real or complex numbers with component-wise linear operations whose norm is defined as shown. And then when P is finite, particularly when P is 2, we get the familiar Euclidean norm. And then when P is infinite, we just have the maximum of the absolute values of the components. And then for LP, instead of n tuples, we're considering sequences, which for a finite P are p-summable sequences. And then the norm is defined here as shown. And then when P is infinite, we have the space L infinity, in which the norm is just the supremum. So for C, we have the space of convergent sequences with infinity norm or supremum norm as defined previously. And for C0, which is the space of converging to zero sequences or vanishing sequences, it's a subspace of C. And then C is a subspace of L infinity. And then finally, we have C00, which is the space of eventually zero sequences, and it's a subspace of C0. And then a Banach space is a norm vector space, which is complete relative to the norm metric, or such that there is for every Cauchy sequence, a sequence such that the distance between the n and m term will vanish as n and m go to infinity independently of each other, which converges to a limit in the space, so the distances from the nth term to the limit will vanish as n goes to infinity. And then revisiting the spaces, we saw the spaces LPN, LP, C, and C0 are Banach spaces, while the space of eventually zero sequences is not a Banach space. And then a Schauder basis or a countable basis of a real or complex Banach space is a countably infinite set in the space, such that for every vector in the space, there is a unique F-term sequence that can be represented as the following series shown here, which is called the Schauder expansion of X. And the coordinates of X are relative to the Schauder basis. And then we see that this differs from an algebraic or Hamel basis, where the basis is not required to be countable for Hamel, and where the representations are in the form of finite linear combinations, as opposed to the series representations that you see here. And then we see that for both spaces LP with a finite P and C0, they have the same standard Schauder basis, whose basis can be defined as the Kronecker delta sequence, and for an arbitrary sequence in the foregoing spaces as shown. And then for C, we'd see that the standard Schauder basis is the set En, which we can obtain by appending E0, the constant sequence, to the prior one. And for an arbitrary X and C, we would have the following series representations, in which the zeroth coordinate is the limit of the sequences, and the other coordinates are the corresponding component terms minus the limit. And then the space L infinity is a Banach space, and it has no Schauder basis. And then a linear operator A from a vector space X to a vector space Y over the scalar field of real or complex numbers is the mapping here, where the domain is a subspace of the space X, and it preserves linear operations. And then if X is Y and the domain is equal to X, we say that A is a linear operator on X. But if Y is F, we say that A is a linear functional. So for our examples, we have that from LPN to LQM, the operator of left multiplication by an m by n matrix with entries from F is a linear operator. And then from LP, we have that the operator of term-wise multiplication by an F-term sequence with a maximal domain shown is also a linear operator. And then either in the space LP, C0, or C00, the backward shift is also a linear operator. And then a bounded linear operator is a linear operator from one norm vector space to another over F, for which the supremum is less than infinity. And then the number you see here is called the norm of the operator A, for which the following holds. And then as a remark, we have that the boundedness in the context of linear operators is equivalent to continuity, even to Lipschitz continuity. And then this takes us to the following inverse mapping theorem, which for two Banach spaces over F, and for the bijective linear operator A from X onto Y, the inverse operator A is a bounded linear operator from Y onto X. So then revisiting our previous examples, we see that they are all bounded linear operators. So for a real or complex Banach space with a Schauder basis, the set of all F-term sequences for which the series converges with term-wise linear operations and the norm defined as the supremum of partial sums is a Banach space, and the linear operator which assigns from every sequence to Y the vector from X, whose Schauder expansion is the series whose coefficients are the term of the sequence, is subject to the inverse mapping theorem that we just saw. And the boundedness of the inverse operator A implies boundedness and hence continuity for linear Schauder coordinate functionals, as shown with the following norm estimates, as well as for the linear operators shown here, where each Sn is corresponding nth partial sum for the Schauder expansion, and then Rn is its remainder. And then here, I is the identity operator, and it can be decomposed into the sum of Sn and Rn. And for the norm of Sn and Rn, we have the following estimates shown here as well. So in norm vector spaces of sequences, term-wise convergence is necessary, but not sufficient enough for convergence. So the natural question to follow would be what conditions are required to be, along with term-wise convergence, necessary and sufficient for convergence of a sequence in such spaces. And so the following characterizations in both proposition 1 and 2 are well known, and they characterize convergence in LP and C0 respectively. And then the following two statements give characterizations of convergence in LP with a finite P and C0 respectively, in which we can see that both statements are two conditioned characterizations. The first condition is term-wise convergence, and the second condition is uniform convergence to 0. And so these two characterizations in LP and C0 suggest that there's a possibility of finding a two-conditioned general characterization, which is as follows. So let X and the norm be a real or complex Banach space with a Schauder basis and the corresponding coordinate functionals. Then for a sequence and vector in this space, the sequence converges to X as n goes to infinity if and only if the following two conditions hold. So moving on to the proof of this, for the only if part of the proof, we suppose that for a sequence and vector in this space, the sequence converges to that vector. Then by the continuity of the Schauder coordinate functionals, we see that condition 1 of the theorem holds. And then for any arbitrary epsilon greater than 0, the following distance between the space and the vector eventually becomes smaller than the right-hand part shown here, which is the norm of the inverse operator that we obtained from the inverse mapping theorem. And then since the vector is in the space and X is the space with a Schauder basis, the remainder will approach 0 and it can be made eventually smaller than the right-hand side. And then in view of prior estimates and by subadditivity of the norm, linearity and boundedness of the operator Rk, we get the following estimates starting for some n, which are at least n big. Then we can see that we get the same estimate for n that is between 1 and n minus 1 because we're dealing with a finite number of remainders of convergent Schauder representations. So we can choose k0 large enough so that we can regard that the finite number of remainders will also be made small. So then we see that it holds for all n, and then thus condition 2 holds, completing the only if part of the proof. So then moving on to the if part of the proof, we suppose that for a sequence and vector, condition 1 and 2 are met. So for an arbitrary epsilon and a natural k0 from condition 2, we then have by condition 1 the following. So eventually all these can be made small. And then since we're in the space with the Schauder basis, the remainder of the Schauder expansion for X is large enough so that the norm of the remainder is less than epsilon over 3. And then by these estimates, we can evaluate the distance from the nth term to X, which by condition 1 and 2 will be less than epsilon. And so thus we have convergence proving the if part of the proof and the entire proof. And these are the following references that were used, and that ties everything up.